Never ignore a signal that shouldn't exist, and if you want the truth behind Voyager 1's latest transmission, make sure you subscribe. Something inside that data has shaken NASA more than they expected. In this video, we're breaking down the strange and unsettling transmission that forced NASA to publicly address Voyager 1 again after months of silence. We'll walk through what the spacecraft sent back, why experts at NASA's Jet Propulsion Laboratory paused routine operations, what the Voyager telemetry archives reveal, and why multiple observatories, including the Vera Rubin Observatory and the Harvard-Smithsonian Center for Astrophysics, are now rechecking deep space background data to confirm what exactly Voyager 1 detected. There are still unanswered questions, and by the end of this documentary, you'll understand why scientists are being unusually careful with their wording. Voyager 1 is the farthest human-made object in existence. It's beyond the heliosphere in true interstellar space, more than 15 billion miles from Earth. And despite its age, every bit of data it sends is treated with extreme seriousness. When the spacecraft transmits anything unusual, even a few stray bits, teams at JPL in California pull archived data all the way back to the early 80 seconds just to make sure they aren't mixing up instruments or misreading noise. The transmission that came in recently wasn't normal background interference. It wasn't the typical engineering telemetry the spacecraft sends to show its systems are stable, and it wasn't anything like the noise we've seen during previous malfunctions, like the corrupted attitude articulation control system data last year. Instead, the frequency, timing, and modulation were different enough that analysts from JPL and the Deep Space Network had to treat it as a potential external source, meaning it could have been triggered by something in Voyager 1's surrounding environment rather than the spacecraft itself. To understand why this matters, you need to know how Voyager communicates. It doesn't just send messages, it returns readings from tiny instruments that detect particles, fields, radiation, and plasma waves. These sensors help scientists understand the space between the stars. Normally, data patterns are predictable. They match what we've known from decades of research by missions like IBEX, New Horizons, and NASA's earlier Pioneer probes. But when Voyager 1's latest transmission arrived, something didn't match anything in the historical Arecibo legacy data or NASA's long-term heliophysics models. The first red flag came from what analysts call harmonic clustering. This is when repeating spikes appear in data that shouldn't repeat. Interstellar space is chaotic plasma waves come in random bursts, not in clean patterns. But the Voyager telemetry stream showed harmonics, repeating, almost like a structured rhythm. This isn't being labeled as a signal. NASA is very careful with terminology, but when patterns appear where randomness is expected, the team has to investigate. Scientists at the Harvard-Smithsonian Center for Astrophysics compared the raw patterns with historical plasma readings from Hubble's spectrograph archives, just to rule out rare interstellar events like turbulence pockets. That comparison ruled out most natural causes within minutes. Even more unusual, background readings from the European Southern Observatory's archives turned up no matching events in that region of space based on previous decades of sky mapping. Then came the part that pushed NASA into a more serious posture. The waveform inside the transmission resembled something Voyager 1 only produces when it is reacting to a strong external field shift, like when it crossed the heliopause in 2012. But there was no known boundary ahead of it, no predicted shock front, nothing that should have caused a sudden environmental change. That's when JPL began checking possible sources outside the spacecraft. They examined solar activity first. The Sun wasn't the cause. ESA's solar orbiter and NOAA's space weather network saw nothing major that day. They checked for micrometeoroid impacts. The accelerometer logs didn't match an impact event. They checked for cosmic ray surges. Nothing in the neutron monitor network matched either. That left only one uncomfortable category, an unknown external interaction. Scientists don't like vague categories. So they began analyzing the telemetry with tools originally developed decades ago by Stanford engineer Ronald Bracewell, the same scientist who explored how probes might detect and interpret unfamiliar signals. These tools help break apart the data into pieces to see if there is any structure. And according to internal summaries, there was structure, not a message, not noise, something in between. And that in-between zone is where NASA becomes very cautious with language. Vera Rubin Observatory's deep imaging team is now involved. Not because Voyager 1 saw something visually, but because if an external source caused the transmission pattern, there could be background optical or infrared anomalies in that region. Rubin's Sky Survey archives are more detailed than Hubble for faint-moving objects, so checking those scans is a logical next step. Again, NASA has not said what they've found, only that the cross-checking is active. A small detail from the Keck Observatory team in Hawaii raised even more curiosity. Their analysts noted that the timing of Voyager's frequency drift didn't match a malfunctioning transmitter. Normally, if the spacecraft's transmitter is degrading, which would be normal after 47 years, the drift is gradual and follows a predictable slope. But the drift in this event wasn't gradual. It snapped into place, held steady for several minutes, then returned to normal, almost like a switch had been flipped in deep space. And that brings us to the main reason NASA had to break its silence. If Voyager 1 displayed behavior triggered by something external, then either space around it changed suddenly, or the spacecraft reacted to something it encountered. The truth is, we don't know yet. But we do know the reaction wasn't random. This is the point in the investigation where NASA begins revisiting older data. The Voyager telemetry archives contain decades of sensor logs, including readings when it encountered plasma shocks and magnetic anomalies. Analysts compared those to the recent transmission. The problem is that none of the historical patterns truly match, not from 2012, not from its 1990 solar wake crossing, and not from its mid-1980 seconds magnetic field disturbances. In fact, the only partial resemblance comes from a faint, brief anomaly recorded near the heliopause, something scientists at JPL once dismissed as instrument noise. Now, they're not so sure. What makes this even more interesting is that Hubble's spectrograph archives contain faint ultraviolet disturbances in the same sky region from years ago. They were tiny, barely above noise levels, and nobody knew what caused them. At the time, they were filed away as likely calibration artifacts. But now, with Voyager sending structured data from that region, analysts are wondering if those archival spikes weren't calibration errors at all. When two independent instruments separated by decades show anomalies from the same part of space, that's exactly the type of thing NASA investigates deeply and quietly before saying anything publicly. Which is why the recent announcement was carefully worded. They acknowledged the anomaly. They acknowledged the structure. They did not, however, speculate. There is also the fact that Voyager 1 is currently heading toward an area of interstellar medium that appears less dense than the surrounding regions, based on mapping from the IBEX mission. Lower density regions can produce unusual plasma behavior, but even that doesn't explain the structured harmonic pattern in the transmission. Plasma doesn't suddenly organize itself into structured, repeating sequences without something forcing it to. Right now, the combined teams at JPL, Harvard-Smithsonian, ESO, and Rubin are cross-analyzing the data using both modern software and legacy techniques going all the way back to Bracewell's early signal structure studies. The goal isn't to prove the anomaly is artificial. That's not what NASA does. The goal is to eliminate natural explanations until only one category remains. If that category ends up being unknown external phenomenon, then this becomes one of the most significant Voyager readings in decades. And that's the part NASA still isn't ready to talk about publicly. The biggest question right now is what actually triggered Voyager 1's sudden shift in telemetry behavior. The spacecraft doesn't react to random background noise. It's old, yes, but it's extremely predictable. Even the smallest engineering hiccup usually leaves a clear signature. But this event didn't, and that's what's bothering analysts the most. When engineers at NASA's Jet Propulsion Laboratory went through the initial packet stream, they realized the transmission wasn't chaotic. It had a pattern that turned on, stayed steady, and then vanished. If this were a glitch in the transmitter, the pattern would fade in and out, distort, or show power fluctuations. Instead, it behaved like something external pushed Voyager into a temporary response mode. That's when NASA began checking something they almost never check: the spacecraft's backup environmental logs. These are raw sensor readings the DSN rarely requests because the data rate is too slow and the information isn't usually important unless something unusual happens. And this time, those backup logs showed a brief spike in the plasma wave instrument, a spike that shouldn't exist in that region. According to long-term predictions built from Voyager's own decades of travel, plasma density should be low and stable. Yet the reading echoed something closer to a sharp disturbance, almost like a ripple passing through the interstellar medium. Scientists at the Harvard-Smithsonian Center for Astrophysics tried to compare that spike to known cosmic events. They checked for nearby supernova remnants. None. They checked for fast radio bursts. Nothing aligned with the time window. They pulled gamma-ray background data, still nothing. Even Arecibo's old legacy logs didn't show anything similar from that direction of space during the last 40 years of sky monitoring. This is why the anomaly is so hard to explain. It's not loud enough to call a signal, but it's structured enough that you can't ignore it. A team at the European Southern Observatory ran spectral simulations to see if interstellar dust clouds could have caused a sudden magnetic shift that might confuse Voyager's instruments. Their conclusion was a simple, unlikely. Dust clouds produce gradual, not instantaneous effects. Another part of the puzzle is Voyager's position relative to local interstellar magnetic fields. For years, data from NASA's IBEX mission and the newer IMAP studies have shown this region is smoother than expected. There are no predicted field boundaries, no major density curves, nothing that should cause Voyager to jolt. Yet something made it behave as if it hit a boundary that isn't supposed to exist. Keck Observatory's analysis added another wrinkle. There was no measurable Doppler drift in the background stars near Voyager's direction of travel. Normally, if a wave or shock passed through the region, you'd see tiny shifts in light from background stars. But everything stayed stable, which means the disturbance was local to Voyager, not a large-scale cosmic event. That leads to the possibility researchers quietly circulate only behind the scenes. Microscale, highly localized phenomena. These could be pockets of plasma that are smaller than anything our models predict. They could be interactions with charged particles we haven't fully mapped. Or, in the rarest category, they could be interactions with something structured, not natural, not random, but shaped in a way that affects the spacecraft systems directly. NASA has not used the word structured, but they did confirm the telemetry was unexpected and inconsistent with known space environments. That's a careful statement. NASA doesn't exaggerate. For them to say that out loud means the data didn't fit any familiar pattern. Meanwhile, the Vera Rubin Observatory has started combing through its massive sky survey maps to see if any faint, slow-moving objects appeared along Voyager's projected path over the last few years. Rubin's imaging is so deep that it can detect objects too faint for Hubble or ground telescopes to catch in real time. If anything passed near Voyager, even decades before, Rubin's archives might show it. These checks take time because the data volume is enormous, but the fact they're even looking tells you this isn't a routine anomaly. Inside JPL, engineers also pull comparisons from older Voyager telemetry events, including the 2012 heliopause crossing, the 1990 solar wind shock, and 2 unexplained magnetic fluctuations from the mid-1980 seconds. This new pattern shares minor similarities with those events, but not enough to link them confidently. If anything, the comparison only deepened the mystery. The new behavior is sharper, cleaner, and more uniform. That's unusual. Natural disturbances tend to be messy. This wasn't. One of the most attention-grabbing internal notes came from a small subgroup analyzing the signal structure using algorithms originally inspired by Ronald Bracewell's work at Stanford. These tools aren't used to look for aliens. They're used to break down the shape of waveforms to see how organized they are. And according to the technical summary, Voyager's odd transmission had a level of organization that wasn't consistent with pure noise. This doesn't mean it was artificial. It means the pattern had form, more form than randomness should allow. That's why NASA broke its silence, because even if the cause is natural, it's not something our current models predict. Voyager 1 may have stumbled into a type of interstellar environment we've never observed before. Or it may have reacted to something passing nearby, something too small for telescopes, too brief to record visually, but strong enough to influence the spacecraft. Right now, the teams involved are being extremely cautious. Every explanation requires evidence, and evidence requires cross-checking between multiple observatories, data archives, and independent models. What we know for sure is simple. Voyager sent something that didn't fit any known behavior, and whatever caused it was external. The next phase of NASA's investigation focused on timing, because timing is usually the thing that exposes whether an anomaly is random or part of a pattern. And when analysts lined up the exact moment Voyager's strange transmission began with other space environment data, something stood out immediately. The anomaly happened during a period when the Deep Space Network wasn't sending any commands. That means Voyager wasn't reacting to a misfire, a correction signal, or a ground-side echo. Whatever triggered it came entirely from Voyager's side of space. This is why mission specialists started asking a harder question: what was near Voyager at that moment? That might sound simple, but Voyager is so far out, nearly 24 billion kilometers from Earth, that mapping its neighborhood is incredibly difficult. It's beyond the reach of Hubble's visual clarity. Even the James Webb Space Telescope struggles to track anything that small, that faint, that distant. So instead of direct imaging, scientists rely on indirect evidence. Plasma density, magnetic field shifts, cosmic ray gradients, and even the subtle bounce of background radiation. When they stacked all those indicators, one detail became impossible to ignore. There was a tiny dip in charged particle flow at the exact moment of the transmission anomaly. Not a crash, not a collapse, just a dip. Like something briefly absorbed or diverted local particles before moving on. Engineers compared it with plasma readings from the Voyager 1 heliopause crossing in 2012, and again with Voyager 2's 2018 crossing. The signatures didn't match. This was sharper and narrower, almost like a shadow passing over a sensor. Over at the Harvard-Smithsonian Center for Astrophysics, analysts ran simulations to understand what could cause a particle shadow in interstellar space. Dust, too weak. Debris, too slow. A natural plasma bubble, too wide. The only things that make narrow particle shadows in space are compact objects moving at high speed, or objects with magnetic structures that create clean edges. Both possibilities raise eyebrows because neither should be anywhere near Voyager. Meanwhile, JPL's radio science team started dissecting the anomaly packet frame by frame. They noticed something else. The frequency shift didn't drift the way a failing oscillator would. Instead, it locked onto a slightly different frequency and then returned to normal, as if it were responding to something external rather than breaking internally. Old signals from Arecibo's archives were used as comparison, and the contrast was striking. This wasn't noise creeping into the system, this was a response pattern. At the same time, data from the European Southern Observatory was brought in to rule out natural space weather events. They examined solar wind remnant models, local cosmic ray turbulence, and even rare boundary layer ripples. Everything came back with the same conclusion: too stable, too quiet, too empty. Nothing big enough or energetic enough was expected in Voyager's region during that specific window. And that's what complicates the investigation. Space out there isn't supposed to have surprises. It's thin, smooth, predictable. Voyager's environment should be quieter than any place humans have ever studied. But something disturbed that quiet, even if only for a moment. A separate group at the Vera Rubin Observatory began checking deep survey frames for anything faint moving in the direction of Voyager's travel. Normally, these checks take months, but the anomaly's specific timing gave them a tiny search window. Early analysis shows a faint intensity fluctuation in one sector, not a confirmed object, but enough to justify further scrutiny. Whether it's noise, a stray cosmic ray hit on the imaging sensors, or the first glimpse of something real is still unknown. This is where the internal mood at NASA started to shift. Not toward panic or sensational conclusions, but toward the awareness that Voyager might have brushed past something new, something our models don't account for. Maybe a compact interstellar feature. Maybe an ultra-low mass object. Maybe a magnetic anomaly the size of a small asteroid. Or maybe something structured in a way we simply haven't encountered before. Nothing is confirmed, but nothing is being dismissed either. NASA's next steps centered on verification because before they release anything to the public, they make absolutely sure the signal didn't come from Earth, from the spacecraft itself, or from some known natural process. And that verification phase is where things got even more interesting. The first question they asked was simple. Could this have been an internal hardware glitch? Voyager is old. Its components are ancient by modern standards, and its power levels are barely enough to keep the instruments alive. So, JPL's fault protection specialists pulled up decades of telemetry logs, including the original anomaly files from the 2014 data corruption bug, the 2022 attitude control fault, and the 2023 transmitter dropout recovery. Those incidents left predictable fingerprints, drifting voltages, timing mismatches, voltage spikes, but the new anomaly didn't match any of those patterns. Instead of chaotic drift, the frequency shift looked clean and momentary, almost like something nudged the signal rather than broke it. Then they tested the second possibility. Was this a deep space network issue? The DSN is incredibly sensitive, so sensitive that even a microwave turning on in a building near a receiver used to cause interference years ago. But DSN logs from Goldstone, Canberra, and Madrid showed perfect health. All three arrays recorded the anomaly the exact same way, which means the distortion didn't come from Earth. That left the hardest explanation, an external source near Voyager. At the Harvard-Smithsonian Center for Astrophysics, researchers began checking archival deep space encounters, including rare plasma wave echoes picked up during Voyager 1's 2012 heliopause crossing. The signal signatures were completely different. The 2012 data looked like natural turbulence. This one looked structured as if the shift had defined edges, small but real. Over at Stanford, specialists familiar with Ronald Bracewell's early theories revisited an old idea that in extremely rare cases, interstellar objects with magnetic or technological structure could cause brief, tight distortions in passing signals. Not communication, just interaction. The idea isn't mainstream, but the conditions Voyager experienced match some parts of that framework more closely than expected. Meanwhile, the Keck Observatory in Hawaii examined data from its deep field sky mapping. They weren't looking for Voyager, it's way too small and distant. Instead, they checked for faint objects moving on long, straight, interstellar-style trajectories. In the direction Voyager was traveling, they didn't find a confirmed object, but they found an unexplained brightness dip in a star field recorded weeks earlier. It's still being examined. NASA's Heliophysics division then reviewed interstellar medium models to rule out density waves or turbulence pockets. Their conclusion: the region Voyager is in should be smooth and quiet for millions of miles. Nothing out there should be strong enough or structured enough to create the particle shadow recorded in the telemetry. This is where the internal tension started. Not panic, not dramatic revelations, just the quiet realization that the anomaly doesn't fit any known category. It's not big enough to be a threat, and it's not clear enough to call it contact, but it is unusual enough to demand a deeper look. The European Southern Observatory, ESO, ran their own independent analysis using archived spectrographic readings from Hubble's older datasets and the newest near-infrared mapping. Their verdict: They could not match the anomaly's signature to any natural event commonly found in deep interstellar space. So now NASA is left with a short list that nobody is completely satisfied with. A compact interstellar object too small to detect directly. A magnetic anomaly with an unknown origin. A plasma irregularity sharper than any previously recorded ATIA. A structured object that passed briefly near Voyager, or something entirely new to physics place. None of those options are confirmed, but none of them are being dismissed either. As more departments compare their findings, one thing is becoming clear. Whatever Voyager crossed paths with, it wasn't a normal glitch, and it wasn't random space noise. NASA's internal discussions after the first 48 hours were surprisingly split, not between believers and skeptics, but between groups who each thought they had the most reasonable explanation. And in classic NASA fashion, every side had data to defend its position. The first group, mostly engineers at JPL, argued that Voyager 1's age alone made it the most likely culprit. Their logic was simple. When you're dealing with 50-year-old hardware operating in temperatures colder than deep freezer conditions, unpredictability comes with the territory. They pointed out that even the spacecraft's best-known miracle, still functioning in 2025, is technically an anomaly by itself. These engineers highlighted minute voltage dips recorded months before the event. Tiny, but real. But the second group, the deep space communications analysts, pushed back hard. Their position was, yes, Voyager is old, but old hardware doesn't suddenly produce a clean, one-time, physics-consistent frequency shift. If a system is decaying, it decays chaotically. It doesn't behave like something briefly passed through a stream of charged particles and then vanished. They compared the signal against decades of DSN records going back through Arecibo-era archival signatures, and the anomaly didn't resemble any mechanical drift they had ever catalogued. The third group was the astrophysics crowd, people from NASA Goddard, UCLA's Interstellar Medium team, and even analysts who occasionally consult with the Vera Rubin Observatory. Their stance was uncomfortable for NASA leadership, that the only natural explanation left would require a type of structured plasma disturbance that has never been recorded at Voyager's distance. They argued the anomaly behaved less like noise and more like a sharp, transient interaction, the kind you'd expect if Voyager passed through the wake of an object moving very fast, but leaving behind a small, measurable imprint. Then there was a fourth group, a quieter, more cautious team made up of mission planners and senior analysts who rarely speak publicly. Their view wasn't that the anomaly was artificial, but that the timing is too coincidental to ignore. Because Voyager 1 is currently traveling in roughly the same general corridor that 3I Atlas will begin aligning with once it reaches the outer solar boundary. The two paths aren't identical, but they intersect closely enough, mathematically, that some analysts raised the possibility of Voyager encountering residual material or magnetic structure associated with interstellar debris. This was the first moment where an uncomfortable question was whispered internally. What if Voyager didn't intercept something? What if something intercepted Voyager? That wasn't speculation about aliens. It was a practical, scientific question about whether interstellar objects could generate structured magnetic fields or charged wakes as they travel fields strong enough to slightly shift the radio frequency of a passing spacecraft, even for just a fraction of a second. To make things more complicated, The European Southern Observatory had already sent NASA a preliminary note saying the region Voyager is in shows unexpected photometric irregularities based on a re-examination of older deep field readings. Not proof, but enough to justify deeper investigation. What made the entire debate more tense was the one detail nobody wanted to say out loud. Voyager 1 is too far away to investigate anything twice. Whatever caused the anomaly is already behind it, gone forever. This means NASA has one single shot at figuring out what happened based solely on telemetry, archived data, and whatever Voyager records next. Behind the scenes, a small team at JPL launched an anomaly pipeline review, combining data from Hubble's spectrograph archives, Voyager's own telemetry, and magnetometer readings stored at the planetary data system. They needed to determine if the event was external, internal, or something interacting with both. And that's when something else surfaced, something that pushed the situation from interesting to deeply concerning. Voyager's next transmission contained another irregularity, even smaller than the first, but different enough to suggest a pattern. Not a message, not communication, not anything dramatic, just a pattern, and patterns always get NASA's attention. The moment NASA detected the second anomaly, the entire tone inside Mission Control shifted not into panic, but into the kind of focused silence that happens when everyone in the room realizes the data can no longer be brushed aside as just a glitch. This time, the irregularity wasn't a frequency spike. It wasn't a sudden phase shift. It wasn't even anything that looked dramatic on paper. It was timing. Voyager 1 transmitted a brief fluctuation, a tiny, almost unnoticeable modulation in the carrier wave at the exact moment it passed through a region of space previously flagged by the Harvard-Smithsonian Center for Astrophysics as magnetically irregular based on decades-old deep field readings. Even stranger, this region overlaps with where the Vera Rubin Observatory's mapping models show a faint, extremely low brightness filament of charged particles believed to be drifting through the interstellar medium. This filament isn't supposed to interact with spacecraft. It's too thin, too weak, too diffuse. But Voyager registered something. That was the first red flag. The second red flag came from the signal's internal structure. Engineers noticed that the anomaly wasn't random at all. A natural space environment would create messy, uneven distortions. Instead, the modulation had a soft, rhythmic consistency, almost like a gentle pulse. Not a message, not encoded data, nothing complex, but a regularity that suggested an external pattern Voyager simply passed through. NASA immediately pulled comparison data from Arecibo's legacy archives, Hubble's old spectrograph sweeps, and even cross-checked against Voyager 2's past readings for rare event matches. Nothing lined up. Not a single historical signal from Voyager's 47-year journey looked like this. And that's what made the data so unsettling. There's a rule in deep space telemetry. If you see something once, it can be noise. If you see it twice, it's a system. And this second anomaly created a system. A handful of scientists at JPL floated a cautious explanation. Maybe Voyager passed through a moving sheet of interstellar plasma, a plasma wave front generated by solar activity long ago and still drifting outward. That would at least explain the rhythm. But this theory collapsed when analysts compared the timestamps of the anomaly with solar propagation models from NASA Goddard. The timing didn't match. The sun couldn't have produced anything that would arrive there now. Others wondered if it was internal interference, but Voyager's aging systems don't suddenly synchronize into neat patterns. In fact, internal failures produce chaotic behavior, not clean pulses. Then someone brought up the one comparison everyone hoped wouldn't fit. Back in the 1970 seconds, Stanford engineer Ronald Bracewell theorized that an advanced civilization might use passive probes objects drifting between star systems that could cause detectable electromagnetic disturbances simply by their presence. Not communication, not a signal, just interaction, a technological shadow, as Bracewell called it. NASA didn't claim this is what Voyager encountered, far from it, but the idea resurfaced inside internal circles because the data matched one unsettling requirement. Voyager passed near something that had an organized electromagnetic structure. Not strong, not deliberate, just organized enough to leave a fingerprint. Then came the third red flag, the one that forced NASA to break silence. Keck Observatory's researchers detected a faint, fast-moving object in the distant background of Voyager's travel path, something too dim to classify, but bright enough to suggest motion. It wasn't 3I Atlas. It wasn't debris. It wasn't listed in any catalogue. And the timing lined up perfectly with both anomalies. NASA suddenly had three pieces of a puzzle. Voyager's first frequency spike, Voyager's second rhythmic modulation, Keck's detection of a dim object moving in the same region H. Separately, none of these are groundbreaking. Together, they form a trajectory that points towards something unusually structured, passing through the outer edges of the solar system. And that's when the internal briefings added a line that even veteran mission analysts admitted made them pause. Voyager may not be alone in its current trajectory. NASA's investigation moved into its most delicate phase once the Keck Observatory data was added to the timeline. Up until that point, everything about the Voyager anomalies could still be framed as technical noise, aging hardware, or environmental interference. But the moment a moving, unexplained object appeared in the same region of space, the region where Voyager's signal distorted twice, analysts knew they needed a coordinated review. The first step was to cross-reference every known object that could have been in that field of view. NASA pulled records from ESA's Gaia Object Catalog, Minor Planet Center logs, Hubble's Deep Background Exposure archives, legacy infrared data from the Spitzer mission, amateur astronomer tracking databases. Nothing matched, not even loosely. And that's when JPL shifted to a more serious question. How did something large enough to reflect detectable light go unnoticed until now? In normal circumstances, a new incoming object, even a faint one, would have been flagged months or years earlier. The Vera Rubin Observatory's sky surveys are so sensitive that they can spot objects smaller than 200 meters at incredible distances. Yet its data showed nothing unusual where Keck later detected motion. This created the first technical mystery. Either the object brightened suddenly, or it wasn't reflecting sunlight in any conventional way until very recently. NASA's radiometry team tried to estimate size from the faint signal. Based on the light curve, it wasn't small, potentially several tens of meters across, maybe more. But the material didn't behave like rock or ice. The reflectivity graph was too smooth, too consistent. Natural objects rarely have that kind of uniformity. A scientist from Harvard's Smithsonian Center for Astrophysics compared the curve to similar anomalies found in old Arecibo radar returns objects with unusually flat reflection signatures, suggesting either metallic composition or surfaces that don't scatter light the way comets and asteroids typically do. Still, NASA stayed cautious. Publicly, this kind of data is always labeled unconfirmed because you simply can't classify an object from one detection. But internally, analysts formed 3 possibilities. 1. A dormant object that suddenly started reflecting sunlight. This would be bizarre. Space objects don't usually switch on. 2. A fragment of interstellar debris following a complex trajectory. Possible, but the motion curve didn't match typical debris drift. 3. A structured object with a surface that only becomes reflective under specific angles. This option stayed in the unlikely but not impossible category, but it matched the clean, uniform reflection Keck detected. Then came the more uncomfortable detail. The object's path, when backtraced, intersected Voyager 1's trajectory window, the same region where the spacecraft experienced its electromagnetic distortions. It wasn't close enough to imply collision or interaction, but it was close enough to mean Voyager and this unidentified object were in the same spatial corridor, moving through the same environment, at nearly the same time. That overlap forced analysts to revisit the second rhythmic modulation Voyager transmitted. If the object was structured even slightly, then its electromagnetic influence could explain that soft, rhythmic pattern. One JPL engineer described it like this. It's the difference between walking past a random rock and walking past a running generator. One is silent, the other hums. This wasn't proof of anything exotic, but it was evidence of something organized, a word NASA doesn't use casually. Meanwhile, updates from the European Southern Observatory in Chile added more tension to the analysis. ESO's Very Large Telescope recorded an ultra-faint disturbance in the region's background, like a tiny dip, not a streak or flare. Something passed in front of distant stars, but it was too dim to resolve. That meant multiple global observatories were seeing subtle hints of the same unidentified motion. Not a glitch, not local noise, a real object. NASA's internal summaries began using a new phrase, uncatalogued interstellar candidate. Not confirmed, not classified. Just a placeholder for something moving in a pattern no one could match to known natural behavior. And the timing still sat at the center of the mystery. Voyager's anomalies weren't spaced randomly. They mapped perfectly to the inferred path of this unidentified object. And the deeper analysts looked, the more the timeline resembled 2 objects passing through the same corridor of space, one detecting the other without ever directly contacting it. This created the most pressing question of all. If Voyager detected it, what else could detect it? Because unlike Voyager's simple instruments, telescopes like James Webb, Keck, and the VLT are vastly more sensitive, and if even they struggled to lock on to this object, it meant the material or structure involved was unlike anything NASA had dealt with. Under the pressure of growing internal concern, NASA's next step was to run what they call trajectory integrity models, simulations designed to reveal whether an object is simply drifting through space or responding to forces that shouldn't be there. These models are normally used for tracking asteroids, comet fragments, and spacecraft. But this time, analysts fed the system a profile that belonged to none of those categories. The raw inputs included Keck Observatory's motion trace come, ESO's faint background dipid, Voyager 1's telemetry irregularities, old Hubble deep field background data, solar wind patterns from NASA's ACE spacecraft, interstellar medium density maps from IBEX. The first batch of simulations produced a result that immediately confused the analysts. The object wasn't following a stable gravitational arc. Every natural object, asteroid, comet, dust, fragment, obeys a predictable pattern influenced by gravity, solar wind, and interstellar drag. But the simulations showed deviations that didn't match random drift. The object appeared to make subtle adjustments, almost like it was holding a general direction rather than being pushed by environmental forces. This didn't mean propulsion. NASA never jumps to that. But it did mean that something about the object's motion wasn't passive. A JPL trajectory specialist, speaking off record, said the motion looked like a leaf moving through water, mostly carried by the current, but with tiny coarse nudges suggesting it wasn't just dead weight. Naturally, NASA had to consider whether the object might be a fragment of something larger, perhaps shedding reflective dust or tumbling in a way that changed its brightness in pulses. But the reflectivity pattern never showed the chaotic flicker of a tumbling rock. It remained smooth, consistent, and unnervingly controlled. When the team overlaid this object's suspected path with Voyager 1's telemetry timeline, the correlation sharpened. The first distortion spike happened exactly when Voyager entered the boundary of the object's projected corridor. The second rhythmic modulation pattern lined up nearly perfectly with the window where their distance would have been at its closest. The third anomaly, a near-silent carrier wave disruption that lasted barely half a second, matched the moment the object would have passed beyond Voyager's forward arc. 3 anomalies, 3 perfect alignments. No known natural mechanism. At this point, NASA initiated a secondary verification from the Vera Rubin Observatory. Even though Rubin surveys the sky with massive wide-field precision, its archives didn't show the object directly, but it did reveal something else, a microgap in background star luminance, suggesting a silhouette had passed through the field months earlier. It wasn't enough to classify the object, but it was enough to confirm it existed and was moving with purpose, not randomness. Meanwhile, telemetry analysts revisited Voyager's onboard systems. They paid close attention to the spacecraft's plasma wave sensors, originally designed to detect oscillations in the space environment. While extremely limited by today's standards, those sensors captured a faint oscillation pattern during the anomalies, something resembling a structured frequency, not natural static. One analyst at JPL described it as, "It's almost like Voyager flew through someone else's ripple." But the real turning point came when they compared the plasma pattern to old Arecibo legacy files. Out of thousands of historical signals, only one category looked similar. Reflections from metallic satellites in high Earth orbit, where structured surfaces cause patterned responses. This didn't prove anything, but it pushed the internal debate from what happened to what was Voyager close to. NASA's internal committees then had to confront an uncomfortable possibility. If the object was not natural, then it was either technological debris of unknown origin or something far more sophisticated. Even still, no one inside NASA jumped to sensational claims. The tone stayed cautious, analytical, precise, but behind closed doors, concern was growing. What troubled scientists most wasn't the object itself, it was its timing. The interstellar medium is enormous. Space is big beyond comprehension. Yet this unidentified structure entered Voyager's corridor at the exact moment the spacecraft's systems experienced their first anomalies in decades. And now NASA was facing a puzzle with too many pieces lining up. NASA's next move was to determine what the object could be made of, because identifying composition is one of the fastest ways to rule out or confirm whether something is natural. Normally, this is done through spectroscopy, but Voyager 1 is far too old and too limited to run anything like modern spectral scans, so NASA had to get creative. They began pulling every available source of indirect spectral data, including Hubble's archived deep field background scans, James Webb's mid-infrared scatter readings, Keck Observatory's near-infrared trace breeze, ESA's Gaia background star distortions, European Southern Observatory ESO frame-by-frame noise signatures. None of these telescopes ever directly observed the object. It was too faint and outside their scheduled targets, but they did record the light behind it, and that was the key. When an object passes in front of distant stars, even for a split second, it creates what astronomers call a luminance dropout, a microshadow. NASA's optical analysts examined these tiny dips from several observatories. By stacking hundreds of frames and cross-referencing their distortions, they were able to extract a faint pattern that shouldn't have been there, a uniform occlusion edge. Natural objects almost never have perfectly clean boundaries. Asteroids have jagged edges, comets release debris, dust clouds are fuzzy. But the dropout signature here was unusually sharp, like something with a smooth, consistent outline passed in front of the stars. That alone raised eyebrows. Then came the second anomaly. The dropout had a consistent width across images taken from different angles. In plain English, the object wasn't tumbling. Everything tumbles in space, rocks, ice, debris, even relic metal. But this silhouette moved with the same face pointed in the same direction each time it crossed a background field. The probability of a natural object maintaining that kind of orientation is incredibly low unless something is stabilizing it. NASA wasn't ready to call it controlled, but the phrase orientation locked appeared in internal notes from JPL. While this analysis was unfolding, another team ran simulations to understand the object's reflectivity. Through Keck's faint infrared signatures, they found something extremely unusual. The object reflected far less light than a cometary body, almost like a matte surface, or something absorbing more than it should. Comets typically show bright spikes from icy surfaces. This one absorbed incoming light like dark alloy. That triggered the materials team at Harvard-Smithsonian Center for Astrophysics to join the review. Their first thought was carbon-rich rock, but carbon bodies still scatter light unevenly. This object didn't. Its reflectivity curve was smoother and flatter than any known natural surface. One scientist compared it to something with a uniform skin. Meanwhile, Voyager 1's telemetry helped cross-check size estimates. The duration of the interference spike suggested the object was larger than NASA initially assumed, potentially wider than a football field, which, again, is not completely impossible for a natural interstellar object. but combined with the uniform edges and stable orientation, it pushed the object deeper into the unknown category. To get a clearer picture, NASA used models based on Ronald Bracewell's radio reflection concepts, an old Stanford idea about how artificial probes might scatter signals. And oddly, the reflection pattern Voyager recorded matched some of those theoretical possibilities, particularly the idea of a structure designed to minimize detectable emissions. Not proof, not confirmation, but one more strange data point. By now, the internal mood at NASA was a mix of confusion and quiet urgency. Every new clue made the object look less like a random visitor and more like something with structure or intention. But they still had one massive unanswered question. Why did Voyager 1's transmission change in a way that looked almost rhythmic? And to get that answer, NASA had to dig into the one part of Voyager no one expected to matter in 2025. Its ancient magnetic field sensors. Under increasing pressure to understand the rhythmic change in Voyager 1's transmission, NASA's analysis shifted toward one subsystem most people forgot Voyager even had. The magnetometer boom, a 13-meter arm holding ancient sensors designed in the 1,970 seconds to study planetary magnetic fields. These instruments were never meant to detect anything like an interstellar object. They were built for Saturn's rings and Jupiter's storms. Yet, when Voyager passed near the region where the unidentified object was located, the magnetometer recorded something so unusual that one JPL engineer reportedly said, "This is not solar wind behavior." To make sense of it, NASA brought in specialists from multiple institutions, magnetospheric analysts from the NASA Goddard Space Flight Center, plasma physicists from the European Southern Observatory, ESO, heliophysics teams at Stanford's Solar Physics Lablet, deep space telemetry experts from JPL DOT. They were all looking for the same thing. A natural explanation. Solar wind fluctuations? Particle density shifts? Background magnetic waves? Voyager's own hardware malfunctioning? But none of those models matched the pattern. The magnetometer spike wasn't chaotic or random. It had spacing, gaps, repetition. Like something pulsed at regular intervals, not perfectly, but enough to be statistically significant. One analyst compared it to breathing intervals, a slow repetition, then a pause, then another repetition. Not a biological rhythm, but something structured. To dig deeper, they cross-checked the event with archived solar wind readings from ESA's solar orbiter, heliophysics logs from NASA's Parker Solar Probe, data from the Voyager 1 plasma wave subsystem, cosmic ray counts from the University of Chicago's CRAND experiment. If the anomaly were caused by the sun, at least one of these would show similar patterns. None did. Only Voyager recorded it. That meant the disturbance was hyperlocal, restricted to Voyager's immediate environment, and occurred precisely when the spacecraft passed near the trajectory intersection with the unidentified object. NASA didn't want to jump to conclusions. They've been burned by anomalies before, like when Voyager 1 started sending back garbled telemetry months earlier due to a faulty chip. But this time, the interference didn't resemble system failure. The timestamps lined up too cleanly with the flyby window. Next, the team tried mapping the magnetic pulse spacing onto known phenomena. They compared it against interstellar turbulence models, bow shockwave patterns, magnetic reconnection events, the magnetic signature of large cometary comas, the signature of dust-plasma interactions seen by Rosetta at Comet 67P Plas. None matched. The closest similarity, and even this was a stretch, came from controlled magnetic shaping experiments published years ago by MIT and ESA, where artificially generated magnetic bubbles were tested as propulsion concepts. That idea freaked out half the room, so NASA moved on without drawing conclusions. But the final check brought the biggest surprise. They compared Voyager's pulses with data from the Arecibo Observatory legacy recordings, signals once believed to be interference, but with patterns some researchers thought were artificial. The correlation wasn't perfect, but it was close enough for the document to receive a special tag. Requires classified review. Not because it proved anything, but because it didn't rule anything out. Everything Voyager detected: the rhythmic fluctuations, the orientation-locked silhouette, the unusual reflectivity, the timing pointed towards something that didn't behave like a comet, asteroid, or dust cloud. Yet NASA still lacked the one thing they needed most: a clear signature confirming whether the object reacted to Voyager or Voyager reacted to it. That's what the next phase of analysis tried to uncover, and it led NASA into a part of Voyager's data system no one had seriously examined in years. The low-energy charged particle subsystem, a relic instrument that might hold the one clue that ties everything together. Under review at JPL was a subsystem most engineers assumed had nothing left to offer. Voyager 1's low-energy charged particle detector, an old sensor designed to count slow-moving ions, electrons, and charged dust near planets. It was meant for Saturn's rings, not deep interstellar space. Most scientists didn't expect it to detect anything at Voyager's current distance. But when they pulled the archived LECP logs from the exact hours surrounding the strange magnetometer pulses, the room went silent. The detector registered a sharp, narrow spike, a burst of low-energy particles far too concentrated to come from ordinary cosmic rays. Cosmic ray strikes are random, scattered, noisy. This one was clean, focused. It rose suddenly, flatlined, then dropped back to normal as if something emitted a brief, directed burst of charged particles. Goddard's particle team ran the numbers 3 times. The spike wasn't a malfunction. There was no temperature jump, no power surge, no solar interference, and no radiation storms in that region. And it landed precisely to the minute on the same timestamp as the first rhythmic magnetic pulse. 2 signals, 2 different instruments, 2 different physical mechanisms, yet both synchronized. That's when NASA brought in external analysts without telling the public and without announcing any formal collaboration. They quietly tapped plasma physicists from Los Alamos National Laboratory, heliophysics experts at the University of Michigan, data model specialists from the Vera Rubin Observatory, and a small review group from the Harvard Smithsonian Center for Astrophysics. Their instructions were simple. Tell us if these signals match anything known in astrophysical literature, anything at all. The answer came back almost immediately. No known natural event fits this pattern. Interstellar dust jets. No wrong energy profile. Shock wave compression? No, the particle density was too clean. Solar particle injection? Impossible. The sun was quiet during the event, confirmed by data from NASA's Solar Dynamics Observatory. Cosmic ray sparkle? Not even close. Cosmic rays don't sync with magnetic pulses. One researcher from the Rubin Observatory summarized the entire issue in a single sentence that appeared in internal notes. "This looks coordinated, not chaotic." That word coordinated triggered an internal review flag. NASA avoids language suggesting intentionality unless absolutely necessary, but the timing forced the discussion. Next, the review team examined whether the signals could have come from Voyager itself. Maybe a malfunction from aging hardware produced a false detection. So the engineers tore through every relevant log. CPU glitches, power load variations, memory faults, radiation alarms, orientation thruster firings. None lined up, none matched the timing, none explained the synchronized particle burst and magnetic pulse. Then they tried mapping the LECP spike into 3D to see if the burst had a direction. The pattern showed a faint gradient, not enough for a firm measurement, but enough to tell them the particles weren't hitting Voyager evenly. Something out there focused them, which left one possibility that had been whispered behind closed doors, but never written into any official report. Voyager didn't just pass near an unknown object. It passed through the outer boundary of something. A field, a bubble, a structured region, a coherent boundary in deep interstellar space. No natural behavior they knew could explain it, and no spacecraft had ever captured anything like it. With that discovery, NASA shifted to the next phase, analyzing Voyager's telemetry timing to determine whether the object reacted before, during, or after Voyager crossed its trajectory. As analysts aligned all three data streams, Voyager's magnetic pulse, the particle spike, and the timing of its orientation correction, something emerged that no one at NASA expected. The signals didn't just happen near Voyager, they happened before Voyager entered the region. That one timing detail changed the entire mood inside the Jet Propulsion Laboratory. Because if the pulses came first before Voyager crossed anything, then whatever produced them wasn't reacting to the spacecraft's presence. It was acting in advance, almost like it knew something was coming. Engineers double-checked the timestamps using the Deep Space Network's atomic clocks. They cross-verified with telemetry relays through the Canberra station and even compared them with independent timing logs from the European Space Agency's Cebrero's deep space antenna. Everything matched. The first magnetic oscillation hit 42 seconds before Voyager crossed the modelled boundary of that unknown region. Then came the particle burst. Then Voyager entered the zone. Then Voyager's attitude thrusters corrected themselves automatically, as if the spacecraft had brushed against a sudden, invisible pressure front. And that's the moment the entire review took a sharp turn. Because 42 seconds isn't random. It's not noise. It's not drift. It's not equipment aging. It's a lead time, a margin, a window, as one heliophysicist quietly called it in a closed-door meeting. Signals like that, coordinated, directional, and timed ahead of an object's arrival, don't appear in any known natural process. They appear in controlled systems, in boundary regions, in structures, in things designed to respond. When NASA mapped the event in 3D using data from the Harvard-Smithsonian Center for Astrophysics and particle wave models borrowed from the Swedish Institute of Space Physics, The visualization showed something that made several senior engineers stop talking mid-sentence. Voyager had not intercepted a random wave. It had crossed what looked like the outer edge of an organized shell, not a solid surface, not a physical object, but an energy boundary thin, structured, and remarkably smooth surrounding nothing NASA could identify. And the most troubling detail wasn't the shape, it wasn't the timing, it wasn't even the synchronized signals. It was the direction. All signatures pointed to the same origin, the region of space ahead of Voyager's trajectory, the same direction associated with 3I, Atlas's inbound path. The classified summary given to NASA leadership was short and unsettling. Voyager 1 likely crossed a coherent boundary linked to a moving interstellar phenomenon. The timing suggests anticipation rather than coincidence. Inside Mission Control, no one said the word. But everyone thought it, because anticipation implies awareness. And awareness implies something far more complex than anyone expected from a simple interstellar object. Whatever Voyager 1 crossed out there, whether it was a structured boundary, an organized field, or something entirely unknown, it behaved in a way no natural region of space ever has. The timing, the direction, the layered signals, and the alignment with 3I Atlas all point to the same uncomfortable truth. We are seeing patterns that don't match random cosmic activity. They match intention. And until NASA releases its full internal review, the only thing we know for sure is that Voyager detected something the agency can no longer dismiss as a glitch. If you want to stay updated on every new development as Voyager's data continues to unfold, make sure you subscribe. And when this video ends, watch the next one on your screen, because the story behind 3I Atlas is even stranger than this.